Good day to you from Galactic. On this last day of February, we're about to enter the new calendar month of March. We are approximately in the middle of Ramadan, and over here you'll see something we've been talking about for the past, well, depending on how long you've been tuned in, for the past few lectures. These are more or less lectures. I don't like that word. I prefer the word presentation, but I need to step up my technology. I do believe in simplicity, directness, and beauty, the fundamental tenets of science from a certain point of view. Make things explicable, understandable, easy. It should be easy because then it's beautiful. You see perfection, you see the symmetries of, oh, really, just beauty, just pure beauty. Well, that should be easy. It's pretty much the opposite of that to open up a book of calculus. So I did deal with the calculus for just a spell there, so you would know that it has extraordinary roots, pardon the pun. The calculus, I did claim in a recent video, is the greatest discovery in the history of mathematics. However, I added a provocative statement, perhaps, provocative of genuine concourse among men, among whom we wish to find our differences for constructive purposes. We need to know what we disagree on in order to make progress. So having disagreements is nothing strange in science or new at all. But in making such outlandish statements, or perhaps off-the-wall statements, one is inciting some kind of, one hopes an insight. The reason a provocative statement is made is because perhaps this is actually leading to something that perhaps we all could enjoy. In the broadest sense, that would be called the truth. We're looking for the truth in science. Now, in geometry, we're looking for a way to see things. And in mathematics, we're looking for a way to prove things. There is a branch of mathematics that applies to making measurements. But really, that's begging the question, you're making measurements for some reason. Well, it's in order to prove a geometry. That is the nature of the Pythagorean theorem, on which I spent perhaps a bit of a tedious amount of time. I'm sorry if I bored anybody, if you did tune in. But I do like to keep these videos self-contained. And the reason we're now looking at our circle in a new context is that every sphere has a peculiar circle called a specific name. Now here in this diagram, I'm just going to let you see what it says on the great circle that you see embedded in what appears to be a sphere by the shading and the drawing of an ellipse inside a perfect circle. That is to show that this is a sphere, through which you can see a diameter in green, and of course the half diameter called the radius, which is simply the radial distance from the center to the surface. But that is the same distance from the center to the great circle. And that could be a great circle dialed, as I like to say, anywhere on that sphere. But here it's shown in the usual orientation, being from our perspective horizontal with respect to the polar axis of the sphere. So whenever you draw a great circle on a sphere, you are simultaneously creating a unique axis, and these dial together. So as you, and you may know this from using a top, spinning a top, which then shows the axis, it's standing upright, but the angular momentum on the circumference of the top's equator keeps it standing upright, which is quite a neat little trick, isn't it? There are certain tricks you can do with bicycle wheels suspended by ropes from the ceiling, which are absolutely flabbergasting because of because of what you're seeing in centrifugal force. And we're going to talk about centrifugal force. There's an interesting problem that comes up in using the words centripetal and centrifugal. And I think you can guess what it is. They sound alike. If you say centripetal, centrifugal, that sounds alike. They sound the same. And as you know, I have a real bugaboo about this sort of thing in science, as when you have a capital O or you have a zero, they look exactly alike. You have a capital I, you have a 1, they look exactly alike, although you can add ornaments to either one. Usually with the capital O, it's put in italics, as we saw from the Wikipedia page. That is a normal convention. But still, I made the case that you should draw an obolus through the O to make a 0, and for the O, you should have a vinculum over the top. We spent quite a while researching those two words because I have problems. I make it my job to have these problems, okay? So when we're talking about this sphere, it does have a great circle, but there is a unique great circle on every sphere, which is a provocative statement. Is that true? Isn't there such a thing as a static sphere? Yes, in geometry there is. You could draw a sphere that has no rotational component at all. But you would have to look a long time throughout the universe to find an actual physical sphere from the quantum level to the cosmological level. Anything that is a sphere is rotating. It has an angular momentum. That, of course, is true of the Earth because we know its spin. And we know that because our spin makes it look like the sun just flies through the sky. In the northern hemisphere, it would be this way, I think, if you're looking north, which you normally would in the northern hemisphere. No, that's not true. Okay. This is provocative stuff. It is a rebasis of the way we do computation. So this is actually going into the theory of mathematics or mathematical theory, which to me just sounds like the most desultory, boring crap imaginable, historically speaking. However, my job is to make even the most dreary, dry, desolate sort of subjects just spring to life because they're easy. And as I began by saying, that should be true in all science. Geometry is no exception. So we're going to get right into the quantum of gravity and the collapse of the wave function, which we began to discuss yesterday, in a brand new way, I hope, that you've never heard before, since everything you're about to hear, I discovered. So that's that's the most provocative statement of all. Well, hang tight because you're in for a ride. That great circle, therefore, could be renamed as the equator. It has a technical name, which I will now teach you because this is a formal presentation. This also will be given at Stanford someday, if the gypsies were right that whispered in my ear. I will be giving lectures on this anywhere in the world, anytime. I imagine it would take 16 to 32 100-minute lectures to complete my full discourse. So I'm open to invitation to anybody who wants to hear this, but you will be the first if you're tuned in here for the first time or not, because nobody's ever heard what you're about to hear. But it's very basic. We're going to take a normal Euclidean logical approach, sequential logic, using the usual tricks of induction to try to make headway against what seems to be an insurmountable barrier. And without going into any negative detail to put a damper on our high spirits today, it has been noticed for a long time now, decades, that it looks like science has painted itself into a corner. Well, it's the job of scientists to unpaint us out of that whatever we painted ourselves into. So the reason we have this sphere with a great circle, which as you can see is simply that circle we were looking at yesterday, that has been encased in a higher dimensional space. And so that circle is now rotated so that it looks like an ellipse. Okay, it looks like an ellipse, but that's supposed to be a perfect circle. And a perfect circle on a sphere is called a great circle. Everyone in trigonometry knows the term great circle. In a geographical or celestial context, that is called the equator. And it would have to be the equator of something. In this case, it's simply the equator of a geometric sphere. So, and that's redundant, but that's to distinguish it from the celestial sphere, which is physical in a more literal way than this simple sphere, which has no celestial labeling at all. It could be the Earth, it could be a proton, it could be a photon, it could be a star, it could be the model of a galaxy. But all these objects have something in common, and that, of course, is they all have a center. Every sphere has a center. And that's quite interesting. The center of something is a coveted balance point. For the sphere, it's particularly coveted because the sphere is defined on that center, and that is reciprocal. They define each other. When you have a sphere, you have a center. And if you have a center, but you know that you're in spherical space, then when you have a center, you have a sphere. But you haven't fully defined the sphere from the center. If you do have a sphere, you only have one center. But if you have a center, you have an infinite number of spheres. Am I correct in saying that? I believe that in a certain context, that is an inassailable statement. If you begin with a center, you have not fully defined a sphere unless you are willing to go into la la land and say that it's all the spheres from that center, which you could say because it is a sentence you could construct. But what you're really saying is, there are an infinite number of spheres. Well, there's at least one. There's at least one sphere if you have a center. And then if you have a preferred sphere for that center, that would have a certain radius. And that's what this diagram tells us. If you have a sphere, which then will have a unique center, then the radius of that sphere is a unique value. So all of that is just indicated very nicely in this simple diagram, which also shows us a diameter. And that covers all the labels, which are 4, on this diagram. We have a center. We have a sphere. So there are actually 5 items here. There are 4 items that relate to the circle. But they all relate to the sphere as well. And the circle relates to the sphere. And that's one thing that you have to say, that the circle is embedded in the sphere, not vice versa. However, if you have a circle on a plane, which is where a circle would live, then you can say that from that circle you have a unique sphere. If you have a sphere, does it have a unique circle? Not in the same way. Why not? Because if you have a circle, it by itself defines a unique sphere. That's not true of the center. If you have a center, you have any number of spheres, right? But if you have a circle, that defines a sphere. So you can define a sphere on a circle, but not on a point. But if you have a sphere, you have a center, but you don't have a specific circle. But if every sphere is rotating, then every sphere has an eigencircle. That is called the eigencircle of a sphere. And it simply means that there is an angular momentum component to every sphere, and when there is, and there always is, then you have an eigencircle. And therefore, because of angular momentum in the universe, which defines centrifugal force, we're getting to the forces involved here, but these are spheric forces. Gravity is a spherical force. The opposite of gravity in terms of directivity, gravity is centrally oriented. We think of it as pulling in. It's a force that, from our perspective, is pulling things into it. That is called a gravitational field. And that is exuded by whatever produces that. I think you can guess it's protons. Protons, when they get together, create a gravitational field. Does one proton generate a gravitational field? Yes, it would have to. Otherwise, it would be very difficult to explain why protons are what give planets weight. Now, there is, as I'm sure you're aware if you are into this sort of thing, a notion that an electron also has weight. And you could even say, using the same logic, that a photon has weight. And essentially, the photoelectric effect, really discovered by Albert Einstein, he got his Nobel Prize for that discovery, shows that light it exhibits force, obviously. In other words, you can drive a light sail boat with light by putting up a sail in outer space. This is actually, there are blueprints for doing this. And you can drive your vehicle by solar wind. It's not really the solar wind, though, which is actually a plasmic force because it's made of particles. But photons are not considered to be particles unless you consider them particles. And in the case of generating force, they do act like particles. Because when they strike the sail will billow, and the ship will sail on the force of a photonic wind. Photonic and protonic are another pair of words where I just my ire rises, especially when I make a blunder, which I'm sorry about that, but it is something a dyslexic person would stumble over, is photon and proton. My God, you just, they sound almost alike. But in any case, that's just a nasty coincidence of the English language, I guess. So that's what we have here. We have 5 objects, a sphere, and now I'm going to teach you that word so that you remember it. Eigen is German for basically unit or one. So eigen really means special in this context. It's a specific example of a higher class. In other words, there are all circles on a sphere, which you could dial, as I say. So that great circle could be in any orientation. But in any actual physical sphere in the universe, there's only one of those. And it's called its eigencircle. I gave it that name, but it's of standard convention. Eigen is used in many contexts. There is also an eigenaxis, and those are called dual objects in geometric argot. And the reason they're called dual is that they occur together. When you have one, you have the other. So in the case of a sphere, you have two things if you have a sphere. Two other objects that you can derive from the sphere. One is its eigencircle, and the other is its center. The eigenaxis we will not be referring to, although it does exist. It's an actual diameter. And that's why the diameter is so important, is because it defines the eigenaxis as a unique diameter. So there's a unique straight line through the center that defines the equator of rotation. And that's another synonym for the eigencircle. And the only reason there is an eigencircle is due to angular momentum in the universe, which is something that has to have an origin. And this becomes very important in the spin of the electron. And as you know, similar computations have been attempted on the proton to see if it has a spin. And I don't know if you know the Standard Model and its use of the word spin, but you can look it up in the Standard Model to find out what any particle has as its spin component. And it's very interesting. This goes into the work of Paul Dirac, who discovered half spin, which is quite significant. Numerically, mathematically, it's quite significant because 1/2 is a most fundamental numeric relationship in the universe, is 1 proportion 2, which we write as 1/2, which we generally, I believe, are taught implies division. In one context, of course, that is really one way of saying it. But as I've pointed out, there are other ways of saying what that relationship is that point out that there's another construction that doesn't use the concept of division. It's perfectly valid, and it would be there's a word for that. I would be overdoing a fine point here if I were to object to saying that. But in any case, despite my necessary preferences for precision, the angular momentum component of a sphere is unique to that sphere. But angular momentum is a very interesting concept because, of course, it's defined entirely on motion. And that is not true of anything else in geometry. Geometry is based on spatial perception, but motion is something that comes from a non-spatial dimension, which is stretching the use of the word dimension. But angular momentum has a time component. You can't have momentum without having a time data type in your definition of that number. That angular momentum has a time quantity explicitly involved in it. Which gets us to the concept of speed. And speed, of course, is related to momentum. And what do these have in common? A lot of concepts are involved. Time, motion. I think you could add to the list, angular momentum is a kind of motion, but it's not Newtonian motion. It's quite interesting to try to describe that kind of motion. We think of it as applying to a solid object. This something can hardly be spinning unless it's rather like the Earth. But when you get down to the atomic level, which in this case would be the electron-proton level. That's the atomic level. When you're talking about the atomic level, you're talking about those two particles. And in this context, it is natural to refer to the electron as a particle, on which point I raise a certain objection, which has been raised before, but I raise it again, is to make the decision of what is a particle and what is not a particle. That is a very interesting and delicate distinction. What I say, and what we're going to be exploring with the help of this diagram, is what exactly is a particle, and do we have more than one definition for what is a particle? And I say absolutely we have more than one definition for what is a particle, but they're hierarchical. They're hierarchical. Can you name, right off the top of your head, the first particle ever discovered? That's a trick question. And I've taught in some of my videos, I teach regularly the precept that you are not required to answer every question. Some questions demand that you use a different strategy of responding, which is not only your right, but maybe your duty in some circumstances to not answer that question. A question can actually be misformulated, and some questions cannot be answered if they're put into the, you would have to say, the wrong context. So it's very important to distinguish between types of questions, and I just asked you a trick question. But it is to raise a delicate point of what is a particle, because that is one of the most confounding questions that we've ever faced. Because of its importance, certainly in nomenclature, when we refer to a particle, do we actually know what we mean? This is highly contextual. I would say yes, but it does need to be extraordinarily carefully defined. And you're just never going to get this kind of a definition from a bot. An AI bot, a chat bot, any kind of robot, any kind of artificial intelligence that will ever be made will not be able to address inductive science, where we're trying to get the answers we really want and need. We are always going to be on our own there, in the sense of getting assistance from artificial intelligence. There is no such thing as that. There is no such thing as artificial intelligence. And it's about time somebody said that. There is no such thing as artificial intelligence. That's a misnomer. All right, my cat needs to go out. The lab cat gets precedence. This will only be a nanosecond for you, but I'll be right back. All right, now the reason for this seeming digression into the nature of a particle is the spheric nature of the particle. And to answer the quiz question that I just proposed to you, just to stimulate thought, what was the first particle that was ever discovered? I would say that you would have to give, to get a complete answer, you would have to go into quite a few steps to answer that question completely. Because there are different definitions for the particle depending on which phase of history you are in. And what has happened is we've found more and more particles which have been misclassified. And that could be debated because that's contextual. The standard model of particle physics is an excellent example. At face value, just bald-faced, that is already a misnomer, because their use of the word particle is quite stretched. And this is not to criticize the standard model of particle physics. whether or not there may be some criticism thereof. This is not to impugn that system in itself. It's to point out that the definition of a particle has definitely changed, and more than once. It's almost as if the definition of the particle has become more and more and more and more particles. But this is really to miss the whole point of the particle, which is quite a pun on the word point, as always, in this sort of situation. The particle has a hierarchical definition, such that you must at some point change the word, just based on lexical considerations for ordinary communication. You're goofing yourself up by using the word particle without really having a firm definition of what you mean by that. And it's not that it's difficult, it's that it's complex. And again, as I started out by saying, my job, as I see it as a science presenter, is to make this easy. Sometimes, though, and I think this is actually a sort of a law of logic or a law of science, that in order to make a convolute or otherwise complicated issue easy, to straighten it out, to give you what you need to know about it so that you understand at least what is being said. That is just basic common sense, is that we just simply want to know, for Christ's sake, just tell me what the devil you mean. And I mean, this is universal. This is a common human foible, is our inability to really walk a tightrope in exhausting a subject properly without unnecessary tedium or detail. And you can see that's almost a contradiction, because you're trying to play two ends against a middle, as they say. And that's what I mean by walking a tightrope. In order to talk about what I want to talk about, which is going to be the quantum of gravity and the collapse of the wave function, the two unanswered questions in physics right now, in one approach. Those are two top questions that are so far unanswered, completely unanswered. So we want those answers, and this is the right framework for approach. Is, first of all, the first particle that was ever discovered is the proton. And in my hierarchy, that is the only particle. That's the only particle. Nothing else is a particle. Only the proton is a particle, for reasons which are so obvious that it's actually kind of spooky that this hasn't been stated more positively as I am now stating it. That if you're going to define what a particle is, there is only one way to begin. You have to define the proton as being the only particle. There are no other particles. Okay, now I've emphasized that enough, and really that takes the place of a proof. No, there's no taking the place of the proof. The hullabaloo, the raising of the voice or the showing of emotionality, is to indicate that you're certain of the proof, so that the audience will be encouraged to listen, because it's going to be something either new or challenging or both. And if it's challenging, it may not be even understandable what's being said. Well, I think you've been in that situation. Try to find out what the actual definition is of the cosmological constant. Or you could even start with the cosmological principle And you will see, as we all must find out if we do this kind of research, that you simply cannot get a straight answer. There are reasons for these strange situations where you just run into calculus. You just run into complex numbers. You just run into gobbledygook. And these men seem to know what they're talking about amongst themselves, but they simply cannot tell anybody outside their clique what the devil they are talking about at all. And that's a real detriment. That's a deficit. Somebody has to fill in that gap. That's what I intend to do. But in order to do so, as you will see, it leads us into the solution space. And this has to do with the Pólya method, justification thereof. That the first step in solving any problem, according to the Pólya method that I learned from that great Czech mathematician and logician, the first step is to clearly state the problem. And when you're talking about the definition of a particle, well, you simply can't even state the problem clearly because you don't know what you're talking about yet. You're looking for the particle. Well, was it discovered? Yes, I say that it was discovered, and it was the first particle in a whole line of particles, as you know now. But where did all these particles come from? And can they be grouped? Can they be classed? Can they be put into some logical structure? Oh, yes, quite simply. So here's the delivery on this aspect so we can get back to this sphere, which, as I'll show you, reveals a lot about the proton, the electron, the atom, and the photon. All can be modeled using this very simple diagram, which now contains angular momentum on the eigencircle. And that has an axis of rotation, which has been discovered at the subatomic level, called spin. And you will read, if you look into this, that spin is not exactly spin in one context. That spin has actually two completely different meanings now, which again is a problem. It's indicative of a confusion. But the key issue here is to define the particle according to a logical structure that will embrace every single particle so far discovered, no matter who is calling the thing a particle. We now accept them all, and we want to classify them now. I will do so for you in the simplest, most economical, terse, logical, complete fashion possible, so that it's coherent, it makes sense to you. You begin by stating, axiomatically you could say, this is the Euclidean approach, to axiomatizing a system, which here is the classification of particles. So how many do we have? There is the proton, there's the electron, there is the photon, there is the neutron, and then there are the subatomic particles. Essentially what began as the neutrino family, as I call it, but it's really the pion, the gluon, the muon, the various signed and unsigned subparticles that come flying out of a proton-proton collision. And these are subparticles. And that's the key to the whole situation, is to be sure that that new class of subparticles are called just that. That's critical. That is not the standard model of particle physics. It's the standard model of subparticle physics. There's more to it, and I may not have said enough, and it may sound like I'm down on the standard model. There is no reason to be down on the standard model. They're simply classifying what they've seen in the bubble chambers, essentially. And they have seen these things. So they do exist. But are they particles? You could say yes, and you could say no, considering that it leaves a trail. None of these are invisible. They actually need to be seen. Or you would have to say, or measured in some way, as for instance, the Higgs boson. It's not to say that these things are unreal. It's to say that you're stretching the use of a good word. When you say that those are particles, they're not. They're simply not. And that's the right answer. Those are not particles. You're just abusing the word. If you say there's no other word, I say you have to make up another word. And it's quite simple. You just prepend a prefix. Sub. And you're done. You've just gotten rid of, by classifying logically, an area that no mortal needs to be interested in unless they find a need to be interested in it. You know why? Because it's complex numbers, it's calculus, it's the strangest kind of mathematics that it takes years to learn. And you can't explain to a novice, a layman, what the hell you're doing. It's obvious that you can't do it. You yourselves can't figure anything out from what you're doing. But the game of science goes on, and the classification part must precede anything else. You have to know what you're talking about. Well, if you use the word particle to describe a muon, a gluon, a pion, or even a neutrino, you are absolutely not following the rules of rhetorical logic. You're abusing the use of words. And I insist on that because the use of the word particle is very important if you start the right way. And this is where it starts to sound, nobody wants to be told off. But if it's important enough, and everything here is important, you must define the particle correctly. You must. You can't be just, oh, well, there's this, that, and the other. What the hell is a particle? It's a proton. And now I can elaborate on that to give you the spooky part in a nutshell so that makes sense. Because there's one other particle. So this is superposition. This is superpositional. If you're going to start correctly in defining a particle, you start out by saying that there is more than one way to define a particle. But if you're going to start with the most obvious, the king of them all, the paradigm for anything called a particle, is a proton, and nothing takes the place of that. Nothing rivals the proton. There's a footnote, though. There's such a thing as a neutron, which is considered to be another particle. Is that true? I say no, but it's superpositional. I would be wrong if I just said no. It's no and yes at the same time. It both is, but it's not. It is if you are Catholic and generous enough to let just anybody into your particle club. Well, the neutron is the first one at the door. Hey, I'm a particle too. I say, no, you're not. You're an altered state of the proton, and therefore the proton needs to be carefully defined at this moment. That the proton has two states, and one of them is the neutronic state, and that is the neutronic state of the only spatial particle that the proton exists in one of two states, but its preferred state, and this has been discovered, a neutron will change into a proton rather quickly, within minutes on the average. But a neutron will only change into a proton for a certain reason, which is still being explored. What makes a neutron turn into a proton? It's a change of state, so something has to cause it. That's quite a fascinating question. But a proton will also turn into a neutron, and that's in a process called beta decay, if I am correct in that. I'm not really an aficionado of this branch of science because my attention span stops when you start talking about stuff the wrong way. So the standard model of particle physics starts out by declaring as their fundamental law of why they exist at all is that everything in the universe is a particle. I don't know if you knew that, but you can look it up. Everything in the universe is a particle. Okay, that's why I don't care about it. But it is important to be able to look at the subject matter and see their eightfold path, as they call it, to make sense out of it to the threshold that you need to say to yourself that you understand it, at least to the point of what is it? What is it? It's a classification of subparticles that were discovered in the Hadron collision experiments, of which there are now dozens. And those are subparticles that don't naturally exist. And I will stick by that, and I will debate that to the death with anybody. So what I'm stating is the truth of the matter, that if you're going to define a particle, you basically have four definitions. One of them is the space particle. That's the proton. And it has a conjugate paired antiparticle. But it's not anti in the sense of being plus minus valent. Although, as you know, it is modeled that way in electrodynamics, that the proton always has a plus to the proportion that the electron always has a minus. That's the measure of something in a linear relationship. It actually has a spherical aspect, which I won't say that I discovered it. I simply am able to classify it so that it can be understood. So we're getting there. If you have, I'm just looking at the time. I'm sorry, this does take a long time to get into the heart of the matter, but it's worth the effort to do this properly because the proton can be represented as this sphere, and I'll show you how that's done. But it's the electron that confounds us. That's where we get all the spookiness. The proton has no real spookiness, such as entanglement, or the technical definition of superposition. That's an electronic concept, strongly related to energy and light, which of course we're talking about the same thing. Energy in the sense of electromotive force. That's the energy that's usually meant. Energy. In other words, the proton does not exhibit energic force. It's a spatial force that it makes that only affects space. The electron does not really even have a spatial presence. Although it does, it's spooky. It's not the same as a proton at all, but they're strongly related. And that's contradictory to what I just said. And this goes to the wave-particle duality. Because a proton, although it has been said that there's such a thing as a matter wave, that really is a technicality. The proton makes a spheric center in space. And that makes our definition of what is a position in space. A position in space is defined at the quantum level as a proton. That's a quantum of space. I can prove that. So that's a fair statement. You may balk at that. Why don't our physicists say that? It's because they can't see it. They can't see that's true. That is the quantum of space, and therefore it is the quantum of gravity. So that is what a proton is. And since it's the quantum of the spatial dimension, that it quantizes space using a force on space called gravitational force, which is a centripetal force that pulls space in. It bends it. It bends it dynamically. But is that energy? That is the hardest question of all to answer. And physics is divided right down the middle on this. Is the proton energy? E equals mc squared should answer that, but it's very interesting to try to define all the terms in relating gravity to the proton, because the proton has as its gravitational component, as far as we can tell, the simple fact that it bends space. And it does, because the electron occupies the bent shell of space at a Lagrangian shell, which I'll get into in the next video. So I hope that tantalizes you. This is, I know it's such a long process, but as I began to say, in order to get through an inductive sequence, all the hard work comes at the beginning. It's almost like setting up a one-line punchline joke with a story that's just quite long. And you get tired because you want the punchline. But in order to get the punchline in a synthetic sequence, which this is, that's the essence of induction, is to synthesize what you already know into a communicable form. That's one way to put it. That's the nature of science, is doing what I'm doing for you now. It requires all the setup in order for the punchline to be effective. And it's worth the wait if you trust the professor. Trust me. Stay tuned. Thank you very much. I appreciate all my listeners. We'll be right back. Thank you.